Okay, let's dive right into this explainer. When we look at academic research, we almost always jump straight to the shiny final statistics, right? But between collecting raw data out in the field and actually getting those insights, well, there lies the true engine room of methodology. We call it data processing. Honestly, think of raw survey data kind of like crude oil. In its original state, it's just this messy, unstructured material full of impurities. Before it can power our analysis, it needs a serious, rigorous refinery. So today, we're going to walk through exactly how that refining process actually works.
Here is our quick roadmap for today. We're going to start by taming the raw data, then move on to editing, coding, classification, and tabulation. And finally, we'll wrap up by looking at how to handle those inevitable processing problems.
All right, part one, taming the raw data. So, raw data straight out of the field, it simply isn't ready for analysis. It is full of weird individual handwriting, blank spaces, and total inconsistencies. Processing isn't just about making things look pretty. It's an absolutely unavoidable prerequisite if you want to draw valid statistical inferences. To actually tame this chaos, we send the data down a sort of methodological assembly line made up of four main operations: editing, coding, classification, and tabulation. Let's look at the very first filter.
Step 2, editing. Field and central.
Editing is basically our strict quality control phase. It's designed to meticulously hunt down errors and omissions so everything is uniform. And this actually happens in two phases. First, you've got field editing. This is rapid, on-the-ground work. An investigator translates scribbled handwriting or weird abbreviations right after an interview, before they completely forget what the person actually meant. Then we have central editing. This is the rigorous office-based scrutiny. A dedicated editor goes through the completed forms looking for inappropriate replies or contradictions. If an answer is obviously wrong or missing, and they just can't deduce what it should be, the editor standardizes it, officially marking it as a no-answer entry.
Step 3, coding. Translating to symbols.
Okay, now that our data is nicely edited, we have to translate all that messy human language into a universal, machine-readable format. That's what coding is. It assigns numbers or symbols to answers. So you might distill 100 different variations of someone saying, "I strongly agree," into just a simple metric, like a 5. But to keep this academically rigorous, these categories have to follow strict rules. They absolutely must be exhaustive, meaning there is a spot for every single data item. They must be mutually exclusive, so one answer fits into one and only one category. And they have to be unidimensional, meaning each class is defined by just one concept. No mixing apples and oranges.
Step 4, classification. Grouping the data.
Even after coding everything, research can leave you with mountains of data volumes. Classification fixes this by reducing everything into homogeneous, manageable groups based on shared characteristics. Now, we hit a really crucial fork in the road here, depending on our data type. First, we have classification by attributes. This is for descriptive, qualitative stuff, things like literacy, religion, or sex, stuff you can't measure with a hard number. On the flip side, we have classification by class intervals. This is for quantitative, numerical characteristics like income or age. Here, the data gets sorted into specific numerical bins. When we're structuring that quantitative data, we can't just wing it. We have to set firm rules for our bins, which we call class intervals. First up, you establish the class limits. That's just your upper and lower boundaries. Next, you figure out the class magnitude, which is quite simply the difference between those upper and lower limits. And finally, you count the class frequency. That's just the total number of items that land inside that specific bin. And hey, statisticians don't just guess how wide these intervals should be. They frequently use something called Sturgis's formula to objectively nail down the perfect magnitude. By taking the total number of observations and the range, this formula makes sure the data is binned in a logical way that actually means something to the analyst. It perfectly prevents those intervals from being way too broad or way too narrow.
Step 5, tabulation. Structuring for analysis. All right, our data is edited, coded, and classified. Now we reach tabulation. This is the orderly arrangement of all that data into neat columns and rows. It takes all our frequencies and summarizes them in a really compact way. Tabulation is absolutely essential because it saves space, makes direct comparisons a breeze, and honestly, it provides the fundamental foundation for computing any further statistics. Without tables, we're literally just staring at an endless sea of numbers.
And this brilliantly illustrates the whole process in action. It shows exactly how we establish our class intervals, like, say, income groups, on one axis, translate the coded responses into simple visual tally marks, and then add up the total class frequency. It is the ultimate systematic visual arrangement of our raw data. It shows you exactly how information is sorted, counted, and completely prepped for the final analytical phase.
Step 6. Handling processing problems.
Okay, but let's be real. Research is almost never flawless, right? Human unpredictability always throws a wrench in the works. And the ultimate methodological headache? The dreaded don't know response. If only a few people say, I don't know, it's easily managed. But if a huge chunk of respondents say it, we've got a major problem. Because you have to ask, is don't know a legitimate answer that shows genuine ignorance on the topic? Or does it mean your questionnaire was just badly designed?
Researchers can't just ignore these anomalies. There are specific academically acceptable workarounds here. You can try to estimate what they meant based on their other answers in the questionnaire. You can isolate them as a completely separate reply category if you think the don't know is a valid stance. You can assume those answers happen randomly and just distribute them proportionally among the other choices. Or in some cases, you can just exclude them entirely from your tabulation. The absolute most important thing here is transparency and statistical safety.
Percentages are another tricky hurdle. They are fantastic for simplifying numbers onto a 0 to 100 scale. But to avoid creating highly misleading standardizations, researchers have to follow some strict rules. Never, ever average percentages together. Always make sure your base sample is actually large enough to be statistically meaningful. And, seriously, always retain the absolute data numbers right alongside the percentage so you don't lose the true context.
All of this painstaking behind-the-scenes work is what actually validates the process. As the guidelines emphasize, it is only through this rigorous editing, coding, classifying, and tabulating that we can confidently subject our data to complex statistical tests of significance. It's truly the only way to genuinely validate whether relationships and differences actually support or conflict with our original hypotheses.
So we build these highly structured, objective assembly lines to process our data. But here is something to think about. Since this entire refinery relies heavily on human judgment at literally every single step, from picking the codes to standardizing an ambiguous answer, what subtle subjective biases might already be baked into the data before the analysis even begins? Keep questioning the methodology, and I'll catch you next time.